So in the previous lectures, I was talking about CKR algorithm, which was a rounding mechanism, a rounding algorithm for multiway cut. But today I want to talk about exponential clocks, which is an alternative to CKR algorithm, a different algorithm for rounding. But before that, let me remind you a duality in the Kalinsky paper. So they had in LP1 formulation, we wanted to minimize the sum of CUV, DUV, such that the distance between two terminals is 1 and DU and V is between 0 and 1. So this is the relaxation. And the LP2 is the same thing, except that we add some extra constraint, which are du and t equal to k minus 1, and also a very interesting and mysterious constraint, which is du and v is greater than du and t minus dv and t. And you will see how this mysterious type constraint, this one and this one, can lead to a dual solution. I mean, LP2, I will show you that it has the same formulation as SLP, which is minimization of CUV dot XU minus XV L1 norm. So it's kind of, you may think that we are getting close to machine learning, because we are going from metrics to a different to norms. I mean, to represent it as an L1 norm, and it may be very interesting. So this is such that xt is equal to et, and by et I mean, for example, if the vertices of this simplex are called, for example, I is equal to 1, 0, 0. Here I could be 0, 1, 0, and another I, which is the third one, which is this one. So when I say I mean that, and E is the coordinate. So ET, for example, could be this, if it is on this terminal. And so any point U that you solve and you want to round it, you always you can write something like this. And it's very interesting that any solution for DUI could lead to this and vice versa. So XIU, it is enough to put 1 minus D of U and I, and then you will see that these two SLP and LP2 are equivalent. In fact, I want to show that LP2 as a proposition, that LP2 and SLP are equivalent. And the proof is very simple. So the proof of this proposition is very simple. So given a feasible solution D to LP2, okay, given a feasible solution D, for example, then we compute the feasible solution to SLP. But how? You just put XIU equal to 1 minus D of U and I, where D is with this. So you see, we want to prove this. So from LP2 constraint, we just write that D of U and I is equal to K minus 1, and this one is just 1 minus XIU. So XIU is this guy. So we conclude that the sum of I over K terminals, which is now 1 minus I over terminal XIU is equal to K minus 1. So this K goes with this, And what is left for us is just xiu is equal to 1, I over terminals. So if you just record this as I, we need another formula as well. So we say that since the distance between u and I is less than 1 and xiu is greater than 0, then, so if you say that this is 2, then from 1 and 2, it is easy to see that xu is delta k, is inside delta k, your simplex. And the next thing is for any u and v in v, now you just write the dual formulation, dual objective, and just because it's just a norm and L1 norm, so you write it as a sum of absolute differences, v and u. And because the d is greater, so this is equal to maximum of 0 and xiu minus xiv. And it's very simple because the d is greater than 0, and we have assumed that if xiu is less than xiv, and then 1 minus the ui is less than 1 minus the vi, we just substitute that. Then we take sum, and then dui is less than dvi, and then dvi minus dui is less than 0 because this is less than dvu, and this is a contradiction. And so that's the reason that now we have solved this, and this is equal to this. So there is no problem here. And after that, we can say that if we define a set such that xiu minus xiv is greater than 0, then this is equal to sum over ins over xiu minus xiv, which is equal to 1 minus dui minus 1 minus dvi, and this is equal to I in S dvni minus duni is less than. So here, because of this constraint that we had, the constraint that we had was d of u and v in the LP2 formulation. D of u and v was just greater than d of u and t minus d of v and t. One of those mysterious constraints that I said. So because of that, this is less than dv and u. And dv and u, you know that it is just d and u and v. So we proved that 1/2 xu minus xv, the L1 norm of that, is less than equal to du and v. And so we get du and v is equal to 1/2 xu minus xv. And so it is proved completely. So you see there is a duality. So solving one of them is like solving the other one. So now that we know that this duality, so why not solve the second one, which is that we times u minus v L1 norm. So we can solve this instead of the original problem. So this is a kind of dual problem, and Ti is now Ei. And this is the people like Niv Buchbinder, a very great researcher, and people like Joseph Sefi Naor, because we had another guy was Naor, And this is another guy. I think that was Asaf Naor, and now this is Joseph Naor. And he's from Technion, and there is another researcher, very, very famous, Roy Schwartz, in Microsoft as well. And they wrote a paper called, in 2013, called Simplex Partitioning via Exponential Clocks and a Multiway Cut Problem. So exponential clocks is just computing independent exponential random variables. For example, xp and lambda, and your distribution is like as a hyperparameter lambda, and then it's like this. And this exponential distribution has some properties. For example, if x is a exponential distribution, then you can scale it, and then it becomes exponential lambda c. We use this for the proof of the theorem. And then x1 to xk be independent, and xi be sampled from exponential distribution. First of all, we can say that minimum of x1 through xk is just, you just write it, xp lambda 1 plus lambda k. So it's very handy and easy. So the probability of xi less than minimum, and j is not I, of xj is just, this probability is just lambda I, lambda 1 plus lambda k, something like softmax that we love in machine learning. So this probability, so what I want to say is that the algorithm that they proposed in that an interesting article is very simple, because you just input your because these are fractions. You have solved your problem, you have solved your optimization, LP optimization, and then these are some fractions. So we want to round it. So it's just a rounding algorithm, just like a CKR algorithm. So we choose IIDZI from exponential distribution. We have k terminals, and the L of u is just, so the assignment to, for example, you should assign each vertex to a different terminal. So it's like a competition, because you want to say that it is the minimum of zi over ui. So minimum of all of these scalars is just a number, and then because argmin is the L of u is just one of those indices, so it's 1, 2, 3, or up to k. So for example, so when I say so this is the algorithm. So when I say ice clock, I mean the I. And z is a vector of exponential clocks. So z1, z2, zk. And zk is a vector of exponential clocks. And so z over sum of zi is a uniformly chosen random point in your simplex delta k. For example, this point or this point. And we should observe that z is the only point in the simplex for which all clocks are equal. All clocks are equal. So this point z is the only point that all, for example, if only two of the scaled clocks are equal, then if you just draw this and then solid to A, and this is your first terminal, your second terminal, your third terminal, what is interesting is that if only two of these k clocks are equal, for example, z2, you see, just notice that we just want to minimize to see which one is the minimum. So if just z2 over u2 is equal to z3 over u3, and then we get that point that We get that point A here, which has a coordinate of 0, z2 over z2 plus z3, and z3, z1 plus z3. So on dashed lines, clock T1 wins. On these dashed lines, clock T1 wins. And on this solid line from Z to A, clock of T2 and T3 both wins. So they are both winners, because Z1 over U1 is greater than Z2 over U2, which is equal to Z3 over U3. So the conclusion is that the solid line is the boundary between the parts assigned to T2 and parts assigned to terminal 3. So in a single lemma, you will see why this is the case, and why this is because we need this lemma to prove for third approximation for the multiway cut. So if we just prove this, then everything is ready. So the lemma, as you see in the article, it says that you have U is equal to U1 up to UK, and V is equal to U1 plus epsilon and U2 minus epsilon, but the rest of the coordinates are just the same. If and of course U and V are in the simplex. If this is true, then the probability that your assignments are the same, are opposite, is less than epsilon 2 minus U1 minus U2. So the proof is very simple. So let I be the event that L of U is equal to L of V equal to I, and the probability that L of U is not L of V, the one that we want to prove, is that it is less than, it is equal to 1 minus I from 1 to K probability of AI. So this AI is just the event that this happens, that they have the same labels and they correspond to the same terminal. So we just need to see what is probability of A1, A2, AI, and then we sum them like this, and then we prove it. So the probability of A1 is just the probability that, so the first terminal, so L of U is equal to L of V, and U and V are assigned to the first terminal. So what is that? It is Z1 over U1, which is less than minimum of Z2 over U2 and ZK over UK. And at the same time, the Z1 over U1 plus epsilon is less than minimum of Z2 U2 minus epsilon and V3 over U3 and ZK over UK. And this probability is the probability of Z1 over U1 is less than minimum of Z2 over U2, and this is just U1 plus UK. So we use the properties of exponential distribution. But similarly, we can say that probability of A2 is U2 minus epsilon. Probability, you can also prove probability of AI is equal to UI 1 over epsilon. And finally, you sum them up. So the sum of all of these, A1, A2, AI. If you just sum them, you will notice that the probability of L of U is not L of